Game's boring. Isn't there out there that's free? Boys, get it?
A large pizza with extra cheese. That's how Peter Watts describes the pilot of an aircraft in his book, Starfish. A square, vanilla box half a meter on a side, twice as thick as your wrist. It was a smart gel, but the characters called it head cheese. Cultured brain cells on a slab. Billions of neurons growing and connected up to a computer. Hardly more than goo and electrodes. You can't program it, but you can teach it, just like any human student. It's the latest in automation and was being used to phase out humans in various professions, including in this case, as pilots. But such a thing couldn't really be made, right? Well, actually it can. Allow me to introduce Head Cheese version 1. Neurons are amazing little creatures that, when grown together, are capable of learning, communicating, and sending signals long distances. Using a mixture of electrical impulses, sudden release of various neurotransmitters, and probably a dozen other mechanisms we're only just beginning to understand, neurons pack a lot of computing power into a very tiny space. Put a few together and you've got enough to control tiny microscopic organisms. A few 100,000 can control a small animal. A few billion and you've got the makings of a sentient intelligence capable of speech, abstract thought, mathematics, and complex decision-making, all contained in something the size of a grapefruit. Now, if you could grow the neurons outside of an organism connected directly to a computer, you could, in theory, use them directly to do a sort of computation and make decisions. This is my homemade electrode array filled with actual human neurons. Today I want to take you through what is probably the craziest and most difficult project I've ever attempted, and required filming in 2 countries and 2 very different labs. Because there are so many parts to this project, the first attempt we'll talk about today was simply to set a baseline. How far could we get before things failed? Could we build the electrode array? Could we keep the neurons alive? Could we get any signal out of them? That's what we set out to find with this experiment. So, no, we won't be flying a plane with this today, but this won't be the last time you hear about this experiment. With everything we've learned from it, and we'll talk about in a moment, we've got a clear set of goals to work towards, and like the spider silk, it'll be one of the big projects we come back to from time to time with updates as we make progress. The idea actually came from a group of researchers that managed to do this successfully. Using custom-made microelectrode arrays, they grew thousands of neurons on a special chip, and then connected it up to a computer. By sending in signals to the chip and listening to the neuron's response, they were able to train tiny petri dishes of rat neurons to fly a plane in a simulation. So let's start from the bottom and work our way up. A few months ago, I built this cool-looking device. It's called a DC sputtering magnetron, and it allows you to coat anything in a thin layer of metal using plasma and vacuum. And yes, it's made out of a jar. For the whole build, I've linked to the previous videos below. In those videos, we explored how we can lay down perfectly flat metallic mirrors or make intricate patterns. For most of the testing of the system, I was using microscope slides as my base layer and coated them in a variety of metals, from silver to copper, gold, and nickel. By first applying a vinyl mask that I prepared with a vinyl cutter, I can shield parts of the glass from the metal plasma and prevent it getting coated in metal. When it's all done and coated, I just peel off the vinyl and am left with an intricate metallic pattern on the glass. After the first of the test-making patterns, I started to wonder if it was possible to make something actually functional with it. Pretty shapes. Sure, I could make a simple electrical circuit, but I wanted something more fun. And as I was thinking about it, I remembered the story about the rat neurons flying a plane. So since then, I've been working to give this a try. The design for the electrode array itself, I whipped up in Inkscape and based it on the original paper's design. I knew I couldn't get the extremely fine resolution that they did with my current setup, as the vinyl is just too coarse, so I went with 16 electrodes that terminated in rounded pads in a grid pattern. The pattern was cut with the vinyl cutter and then covered with green tape to hold everything in place while the pattern is transferred to the glass microscope slide. Then, after trimming the design, all the areas where the electrodes would be had the vinyl removed. I repeated this with a bunch more microscope slides, as I wanted to have as many of these as I could. And it's a good thing that I did, because only one array survived the whole process from plasma to cell culture. One at a time, the prepared slides were coated first with a layer of silver and then with a layer of gold. I let the silver layer grow for as long as possible so that the extremely thin wires would be as conductive as possible to make taking readings easier. The gold top coat makes everything more biocompatible so that it's safe to grow the neurons on the electrodes. We'll talk more about this later, but my material selection here, as well as the lack of any pretreatments to the glass, gave a bunch of problems down the line, so future versions will use a different material and treatments for this step. Because this was the first test, the thick electrodes and the fact that the entire electrode is exposed to the culture solution is fine. But for future iterations, another step will be to coat everything but the very tips of the electrodes in an insulator, so the readings come from a more distinct area. And then switching from a vinyl mask to photoresist would allow for more and thinner electrodes to be made. With the slides coated in metal and the vinyl removed, I was left with 4 arrays of acceptable quality, and so these could be turned into petri dishes. To do that, I started with 15 milliliter Falcon tubes and used my lathe to cut off the very top. This is now a threaded piece of autoclavable plastic, which, once stuck to the microscope slide, will make perfect little petri dishes. To attach the piece of plastic to the glass, I picked up some FDA-approved implant-grade 2-part epoxy from Atom Adhesives. This stuff is autoclavable and biosafe, so you could use it for something implanted into someone and it would remain inert and safe. Before this gluing step, I cleaned everything off camera and brought all the slides into the biolab, so I had a clean, dust-free workspace. The epoxy is activated by popping the internal separator of the packet and then mixing thoroughly. I used a long, sterile swab to coat the piece of Falcon tube, which was then carefully placed onto a patterned microscope slide. Once these cured, the electrode arrays are basically done and ready for neurons. The lids can be carefully screwed on to keep the liquid protected, and opened easily to work with the cells. The finished arrays were then packed up and shipped to Indiana and my good friend Gabriel Lacina's lab. If you don't know Gabe, he's a biologist that's done some really cool projects over the years. Recently you saw another project I filmed at his lab where we turned a grape into a meatberry. He's doing a lot of cool stuff, which we'll talk about in future videos, but I've linked to his pages below if you're interested. His day-to-day work involves working with mammalian cells, so his lab is set up to grow things like the monkey cells we used in the meatberry video, or in our case, human neurons. Speaking of which, for the neurons, we had a few different options from different suppliers online, but I wanted healthy human neurons which ranged from holy oh my god my wallet is on fire, to still fairly expensive but not as bad. We went with mixed cortical neurons, which were derived from induced pluripotent stem cells. That's a lot of big bio words that probably don't mean anything to most of you, so let's break that down. Mixed cortical neurons means that it's a mixture of 2 different types of neurons that are normally found in the cerebral cortex of the brain. The 2 types here are glutamatergic and GABAergic, which refer to the neurotransmitter that they interact with. In this case, glutamine and GABA, respectively. They're in about a 20 to 80 ratio, likely taken from a pure stock of each and literally just mixed in a tube before they're sent out. The induced pluripotent stem cell thing refers to how the neurons were created. They weren't harvested from a living organism, or at the least, they didn't start as neurons. That would be what's called primary cortical neurons, which refer to them being freshly harvested from something rather than lab created. To make them, scientists start with one of a variety of cell types from some organism. Lots have been used, but honestly it doesn't really matter that much. Let's say skin cells from a person, for example, or as we normally call them, human fibroblasts. To turn fibroblasts into stem cells, you first get them growing in a culture flask like we've shown in previous videos. Then you transfect them, which means you take a piece of DNA and put it into the cells. That special piece of DNA is readily available and something you buy pre-made. It's a little circle of DNA that once it's inside the cell, kicks on 4 different proteins. These set off a massive symphony of biochemical pathways in the cell that makes it revert back to a stem cell-like form. What is a stem cell? Well, normally these are sort of your base level cells. They can make essentially infinite copies of themselves and can differentiate to become any other cell type in theory. Once you've got stem cells, you can use different molecules to trigger the differentiation process, and if you deliver the right triggers at the right time, you end up with a cell type you want. In this case, the 2 neuron types we just talked about. These cells are a terminal cell line, so they shouldn't divide anymore, so however many neurons you have in the tube is the number you have to work with. For our experiment, we purchased the smallest available quantity, which was 1 million, and came in this tiny tube. To allow the neurons to grow, we need special growth media for them. This will contain all the nutrients and other chemicals that they need to survive. We went with neural basal media and a B27 supplement from Thermo Fisher. The supplement should contain a variety of different growth factors and hormones, like nerve growth factor, to keep the neurons happy. We also added glutamine as the protocol for the media preparation called for it. And finally, we added antibiotics to make sure that the neurons were protected from any bacterial contamination. I'd tell you more about what's in the media, but honestly, it's such a witch's brew of stuff that I really don't know what a lot of it is or does, and just followed the recipe on the site I bought it from. Before we can put any neurons into the electrode arrays, we first need to add an air filter to them to allow the cells to breathe, and then sterilize them so they're clean and won't contaminate the neurons. The filters I made out of these Luer-Lock syringe filters that I normally use to sterilize media. The pores are small enough to prevent anything from getting in, but will let air through. These are epoxied into pre-drilled holes